so basically this session is gonna be pretty like hands-on. So I'm not really gonna lecture too much, but I'm just gonna I'm gonna put up some problems that I think help us learn like the different things that, the different ways we can affect the performance of our cars in Baja and Formula. I've never done the breakout sessions, but we'll try some of those. But so I'm going to be kind of winging most of this. So there'll be a lot of mistakes and stuff. So definitely keep your eye out. It's not meant to be just, go play Borderlands with this on in the background type of thing. So you're actually going to be
Forza.
Figuring out what's the game you guys play now?
It's Forza.
I don't know what that is.
Yo, you should play too.
No, I
You should. We could rally. Come on.
Enough distractions. All right. So I guess other just like common things, like if you're not talking, if you're like going to be dead silent, that's fine. But if you're not talking, you might have people around you, like put your mic on silent so we don't get like a ton of background noise coming through here. Other stuff, if you put up the participants, you can like raise and lower your hand and stuff. If you bring up the chat, you can put stuff up in the chat, or you can message stuff just to specific people if you want. So we'll start with that. Anyways, all right. So any engineering workshop wouldn't be complete without first talking about forces on the car. So, all right. So I'm going to do my best to like draw somewhat nicely and not like do that too many times. So let's see. We got some road. Let's draw something that's halfway between a Baja and between a Formula car. That's a Formula car right there. All right. So this thing's driving down the road. What are the forces on our car? Right. So just you can yell a couple out.
Normal force.
All right. So we got a normal force. So we'll say let's say normal in the rear, right? And then we'll have a normal in the front, right? Oops. So we got these two. All right, so we got those two keeping the car falling from the ground. All right, what else we got?
Friction.
Friction, baby.
Friction. All right, so is friction slowing us down or making us go forward? What's this friction you're talking about?
Making us go forward.
All right, so there's a force in both of our cars, the rear tires and the ground, making us go forward. So we have the force on our tires. Right? All right, so that's making us go forward. What else we got?
Wheels.
Yeah, we got wheels.
The weight.
Okay, we got a weight, right? So we got a CG somewhere. And we have the weight of the car right here. Okay. What else we got?
Air resistance.
Yeah, we got air resistance. So we have some sort of drag force on the car, right? That looks good. What else we got? Sergio's here. I know Sergio knows this. Where's Sergio at?
I'm here. So we also have friction that's slowing us down.
Yeah, you got like rolling resistance, right?
Yeah, rolling resistance.
So your wheel bearings, all your driveline stuff, your tires are having to deflect and undeflect, right? And so that's also, you lose energy there. So you actually will have, it's not applied up here, but we have another force of rolling resistance, right? All right, so this is not all, but I guess, but I think this is kind of the most common forces that are on the car, right? So, I mean, we're kind of racing. So in essence, we basically want to be accelerating forward or decelerating as fast as possible at all times, basically. Going between slow enough to go around corners and up to our top speed in the straightaways, right? So we basically just want to go as fast as possible for as long as possible, slow down as quickly as possible in the turn, and then get back up to speed, right? So the name of the game is kind of acceleration here. So if we're going to use Newton's laws, right? So we'll say sum of the forces, and I'm going to make an x direction here and a y direction. So we have sum of the forces in the x direction. You're going to equal to the mass times the acceleration in the x direction, right? And so we have the force on the tires making us go forward. We have the force of the rolling resistance making us go backwards. And we have the force of drag making us go backwards. Everybody with me so far?
Yeah.
Yes.
Yeah.
All right.
Sure.
So this is basically what helps. These forces are going to govern how quickly we can go from high to low speeds, basically. And I guess the force of the tire is a little bit more complex because it could be resulting from the brakes, it could be resulting from the drive line, right? So there's a lot of different things that the force of the tire could be influenced by, right? So we'll leave that for now. Let's start with some of the ones that we can kind of more quickly get a handle on. So we have the force of rolling resistance. So what's a good estimate for the force of the rolling resistance? How do we usually describe this? Someone's got cartoons on in the background, muted at least.
Alvin.
Oh, Juan.
Alvin, what are you talking about, dude?
All right. Anybody got an idea? How do we, I know Sergio might know this. Anyways.
What were you asking me? I'm sorry.
What is governed by what are some things that affect the rolling resistance?
Ooh, rotational inertia.
Higher pressure?
Yeah.
Coefficient of friction.
More
Friction.
simple. What's the simplest model we can make for this bad boy?
So you're looking at an additional 200
So I'll give it to you guys. So there's what we call is there's a coefficient of rolling resistance, and this gets this rolling resistance gets related to the normal force, right? So we'll say the coefficient of rolling resistance, and we'll say it's times N rear plus N front, right? And those two are just going to be equal to the weight. So you can decrease this value by decreasing this kind of coefficient or decreasing the normal forces, is kind of how we break it up. So let's talk about the drag force. Right. So the drag force, what's the force of drag? This is, and we're in a high Reynolds number. Much greater than 1. For you kids that took fluid mechanics, you know, like, you're dominated by inertial forces. So don't like give me some Stokes drag type thing. How do you break down this drag into?
Area of the front of the car.
Got you. Some frontal area cross section. I'll throw a half in there for you. This is an area, not a delta. What else you got?
Velocity of the car.
Velocity to the first power.
Squared.
Yeah, velocity squared, right? So which one of these forces do you think has a bigger effect at high speeds?
Velocity because it's squared.
The drag way over rolling resistance, right? I mean, that's why Formula One, right? Name of the game is aero, right? Packages. I mean, this force is huge at high speeds, basically. So, and they go fast. All right, there's some other stuff must affect it, right? I mean, does the viscosity affect it? Maybe the density, right? I mean,
Temperature of the air.
temperature, okay. You guys must have, I mean, you guys must have seen this equation before.
We haven't
Right.
gotten to it yet.
Yeah.
I mean,
haven't gotten
if someone if someone was an aero guy, right, and you're gonna ask them something about a car, you know, and you were like, oh, how good did you make this value? There's probably one thing you'd ask for. You'd ask probably for the drag coefficient, right? I mean, you guys have heard that a billion times, right? It's got a
Yeah.
drag coefficient. Everyone's designing how low can we get this drag coefficient, right? You got a drag coefficient. And because it's inertia, it's high Reynolds number. That means density plays a larger effect than the viscosity, right? So that's why density is in here. You have some low Reynolds number flow, some very slow flows. Viscosity plays a bigger role. And you'll see viscosity will be in here. Okay. So we see we want to decrease the frontal area. We want to decrease the drag coefficient. We can't touch the density. And well, we're going to want to go fast, so we can't really touch the velocity that much, right? So, but we can touch the drag coefficient and the frontal area. Okay. So if I multiply this force on the tire by the velocity at which we're going, someone know that of an important parameter that that's related to?
Work.
It's work. It's good. It's a power. Power of what? I mean, there's only one thing that drives your car, basically.
The engine?
Yeah, this is the power of the engine. So this value right here is your engine power. I mean, there's going to be some losses and, you know, through the drivetrain and all that stuff, right? But this is the effective output of your engine, basically. All right, so this is your engine power. So if we take this, I'm going to just rearrange this top equation right here for Ft. So I'm just going to rearrange it for Ft, and I'm going to multiply this whole thing by velocity. Oh, that's not good. Let me try this real quick. Computer's really thinking. There we go. All right, we're back. So we're going to rearrange this equation, solve for Ft, then we're going to multiply by the velocity. So over here is Ft times velocity. So when I move everything over, I have mass times acceleration times velocity. And I have plus, I have mu r times the weight times the velocity, plus 1/2 area front CD rho v cubed. So what do you think eats up the power of your engine at high speeds? Wild guess? Throw it out there.
Definitely your air resistance.
Yeah, it's velocity cubed, right? Like you're going high speed. This term is killing everything else, right? High speeds, you're not accelerating maybe that much either. So this mass times acceleration term is a little bit small. So this is like dominant at high speeds. This is a high speed term. Right? And what term do you think is probably pretty dominant at low speeds when you're trying to get going fast? So you're usually accelerating. It's probably this term. This is probably more dominant at low speeds. Hopefully you can engineer the rolling resistance out of your car, basically, right? I mean, hopefully you get this coefficient of rolling resistance to like 0.01, you know, in the case of formula. Right, so you can get that out of here. But the drag coefficient's really hard to get super low, right? I mean, especially we're so limited with our firewalls. I mean, we're basically driving around a kite, basically. The nice part is none of us go very fast. So to be honest with you, maybe for us, you know, our high speeds are like 35 miles an hour. So maybe this V cubed is not a super big deal. Okay, so this is kind of a lot of the stuff that you need to know wrapped into a nutshell about straight line driving. We're not talking about turning yet, right? So this is you know, we're going in a straight line. What are the forces on it? So I guess my question for us to work on now is, let's see here. So for both of the teams, I guess the question is, let's say you design everything perfectly. What is the best acceleration time we can begin to hope for? This is actually a pretty complex question. I mean, it's basically the simplest dynamic event that we do. And we're not even trying to simulate exactly what the time's going to be, but what's the best we could do? And once we figure that out, we can see what kind of governs the best we can do. And that tells us a little bit about the knobs that we can tweak on our designs to try and get there, basically, right? So I'm going to scroll down a little bit. All right, so you guys know more about this than me, but so here's some of our cars. Basically, I got Baja stats on the left. I got formula stats on the right. And so you guys correct me if it's wrong. So for a car on the side view, you have the CG in this plane, and there's a length from the back tire to the CG horizontally. The length horizontally here. There's a height of the center of gravity. In the top view, you have your CG, and you can see the length again here. And you have a wheelbase from center tire to center tire, and then you have a track width from right tire to left tire. So I don't know, I'm estimating the track width of the Baja car is 58 inches on average, basically.
Sure.
Formula, it's a little less, maybe 55 inches. I don't know, Patrick, you can tell us maybe, or Renee.
It's 51.
We got 51. Okay, and then both wheelbases are about 60 inches, right? Is that right?
Yeah. About.
I mean, this don't need to be exact. We're
Yeah.
in the ballpark basically, right? We have our height of our CG. We don't know either of these values, to be honest, but my best guess is Baja's up over 12 inches, basically sitting in the driver's butt. And is that David? At least mute yourself if you're coming late.
No, that's not me, but
No,
yeah, I'm
okay.
here.
Okay, good. And then the CG, I'm just guessing for formula is about 8 inches. So the wheel balances for the Baja car, our current car, looks like this. This is the front left, front right, rear left, rear right. Here I'm estimating the formula car's wheel balances. We run a little heavier. Engine power, we have about a 10 horsepower engine on Baja with maybe best case scenario. Well, hopefully we get 60 in formula. So here's some plots of, you know, well, I should actually this is negative slip ratio. So for a tire going forward, this normalized longitudinal force, this is the force on the tire divided by the normal force. And you can see on this right graph, so positive slip ratios, so we haven't talked about what a slip ratio is, but a positive slip ratio is driving forward. So your tire actually spins a little bit faster than the ground goes by. So, you know, if you had a tire rotating on the ground, and you had its center, and you were curious, how does the velocity of the tire relate to its angular speed? You would typically say, oh, well, this velocity is going to be equal to the radius times the angular speed of the tire. So that's not completely true. The tire actually spins a little bit faster than it goes by on the ground. And that's one, it slips slightly, and two, it's deflecting the tire. You know, the tire is actually getting pulled back as it's driving it forward, right? So, so like, for example, this tire is driving forward. You know, this tire is actually going to be deflecting this direction, right? As it drives itself forward. And then it's going to unspring itself. As it gets to here, it unsprings itself, right? So you're kind of like unspringing the tire back and forth. I mean, one resistance for the rolling resistance and the slip ratio, but we don't really care about that too much yet. What we care about is the maximum value for driving. So when you see this normalized, this value, it depends on the downforce. So this is the varying downforce. This is at inclination angle of 0 camber, a 12 psi, and this is our formula tire. So we're about 200 pounds force on our rear. We're 195. So we're looking at maybe a normalized longitudinal force of 2.5, basically. Baja, we're in the dirt. So my best guess, based on Sergio's measurements, actually, is that our best normalized longitudinal force that we can get is basically 1.2. And you can think about this. This is like the coefficient of friction before your tire starts to slip, basically. And when I say slip, I basically mean like start to lose contact with the ground, right? So at some point, you drive your tires so hard that they start to spin on the ground, right? So you can't put an infinite number of force, right? So this value is quantifying that, right? So maybe what happened to our 0, 1? So I don't know. Sergio measured our rolling resistance of our car as 0.17. Seems crazy high to me. Should be down here. It should be, but we're in the dirt, so maybe it makes sense. Our brakes weren't that good last year. This is on last year's car, and this is here. And here's some of the drag specs, basically, for our cars.
I have a quick question.
That's the estimate. Yeah.
So on that graph, everything that's like, it gives you a line and stuff, but once that line disappears or whatever, that's pretty much when your wheel's slipping or like there's no traction at all.
Yeah, I mean, so you see the left-hand side is braking, the right side is going forward. So you see they kind of reach a maximum at 0.1. So if you went any further, you would start to spin the tires on the test, basically. So yeah, so you can't really drive them any further. They would come back into the left, basically, because the tire has more friction when it's not slipping. So it would actually go down and back to the left down here. That's what it would do.
Okay, thank you.
So yeah, so this is but it's a lot. I did not guess that our tires were this sticky. I mean, this is like having a coefficient of friction of 3, right? I mean, these things are basically like glue on the asphalt. And this is not tested on asphalt though. This is testing on 3M has some compound they put on these tire testing machines that they think is similar to asphalt. I haven't actually seen good data on that, but so what I'm gonna do now.
At a certain temperature, right?
What?
This is at a certain temperature as well?
Yeah.
Like it just,
Yep.
it could change.
Yeah, but I mean, you get it up to your operating temperature, right? So they test this at, they basically test everything at their operating. So they have a warm-up period, gets it up to its operating temperature, and does it and then does all the testing at the operating temperature. Okay, so I'm gonna try and put you in groups. And so we're answering this question. I've never even done the breakout groups. We're asking, what is the best Excel time that we could possibly hope for on both of our cars, right? And I think, Baja, I think we do like, what do we do, 100-foot Excel? I think Formula is about a 246-foot acceleration run, right? So let's see here. Let's try some breakout groups. So if you design your car right, and you design your car with enough torque in low gear, you should be able to spin the tires, basically. So the only thing that should be, so at this point, we haven't designed our gearbox, nothing. The
Right.
only thing that should be limiting you is the tire friction between you and the ground. You should be what we
Right.
call traction limited. So
Yeah.
basically, this force that you can produce with the traction on your wheels will be what can help you accelerate at this point. So for example, like we should design our gearbox to slightly, you know, if we wanted to spin the wheels, we could spin the wheels, but a good driver would know not to stay just under that.
Oh, okay.
Right. You feather the throttle.
Exactly. You should be able to get it going without spinning the wheels, basically. So the max force you can get going forward, in my mind for Baja, it's going to be 1.2 times whatever wheels times the downforce on whatever wheels are doing the driving. Same thing with formula, right? The max they can get, they got a lot stickier wheels. You should be able to maybe get around 2.2, 2.3 times the downforce, times the downforce on the wheels that are doing the driving, right?
And that was that graph right here.
And that's this graph.
Data that they showed.
This is
It's-
data from the tire consortium.
Yeah, but like you could use those values essentially, or
Yeah, you should. Well, first,
just
we just
got-
talked about the forces on the car.
Oh, I got that.
Okay.
So we talked about.
That's what I was talking about, David.
We talked about the rolling resistance, the drag, the force on the tire. Talked about how we could break down the rolling resistance into coefficient of rolling resistance times the two normal forces, the drag at high Reynolds numbers, and then we related these values to the power of our engine. And we basically said that at low speeds, this acceleration term is going to dominate. At high speeds, our drag's going to dominate. And then we talked about the different rough properties of the cars. And now we're going to see what we can do with it all. All right, everybody back?
Yeah.
All right. We got any ideas about how to start?
Yeah, Yee's got some stuff.
All right, what you got, you?
I can share my screen. Give me a second.
Yeah. Let me unshare mine.
So like we just did some like, I guess like kinematic equation pretty much.
Got you.
This is a main equation we use. And he said the acceleration zone for Baja is 100 feet. So we assume D is equal to 100 feet. VI is going to be equal to 0 because we're starting from a standstill. So I isolated my equation. So I get time equal to 200 feet over final velocity. And I asked Juan, what's like a reasonable final velocity? And he said it's a 25 miles per hour. That pretty much converts to 36.67 feet per second. So we got our time, I guess, best scenario time is 5.45 seconds or 5.5 seconds.
Okay. All right, that's something. You're in the ballpark.
Oh, okay.
I mean, but let's.
But yeah.
Okay, I'm gonna unshare your screen. Any other
Okay.
ideas? I'm sure no one else did that. So if you had anything, you had something that wasn't that. All right, let me share my screen. I mean, so this was what your model was. You basically said, okay, we think our velocity is as a function of time. So we're just gonna have a linear acceleration starting from 0 to 25 miles per hour, right? And you said, how long would it take us to go 100 feet doing that, right? So that's basically your model, right? Which is fine. I mean, we do this in about 4 seconds. So you're off by 25, 30%, you know? So that's reasonable. It gets you in the ballpark. Doesn't help you that much with design though, right? Because that 25 was based on experiments. So let's see let's see how maybe I would approach this problem. So I basically know the most force I can put into this ground right now, and we call that being traction limited. When we're limited by how much traction we have with the ground. For Baja, it's going to be 1.2 times the downforce of our driving wheels. Right? So this is basically how much, this is basically a coefficient of friction, right? So so let's do, I'm trying to think which one should I do. Let's do formula. Formula will be more fun for Excel. We get a little faster. So the max force. So actually, we got to start off with a car first. We have a car that looks like this. We have the normal force in the rear. We have the normal force in the front. We have the CG somewhere here. We have the force here. Right? So, and this is the force on the tire. So the max force we can get on the tire to help drive us forward is going to be, I'm going to call this normalized force in the x direction, max. Right? So this was our what was it? This was, for going forward, this was up here. This was about negative 2.5 maybe. Let's just round it to that. So this is 2.5 times the downward force in the rear. Okay? So the downward force in the rear on the formula car is 195 times 2. We have these two tires are driving us. None of this helps us. This 130s in the front don't help us one lick. So what we basically have is our max force that we can drive us forward with. It's going to be equal to 2.5 times the normal force in the rear. So that's going to be 195 pounds force times 2. Right? So anybody got a calculator on them? They can. I got mine.
Chris, where'd you get that 195? Is that the weight?
So if we put the scales on the formula car, to my best guess, this is what the 4 corner weights would look like of our formula car.
975.
That'd be 260 and roughly 660, 650.
650 with a weight distribution of 60-40.
Okay.
Best guess without a car. So what do we got?
So 975.
975 pounds force. That's the most we can drive forward with. Best we can hope for. Right? So with that force, how much can we accelerate? So we say this FT max is going to be equal to the mass of the car, right, times the acceleration max. Right, now we can find what's our max acceleration. So A max is going to be equal to 975 pounds force driving us forward over the mass, which will be 650 pounds force divided by 32.2 feet per second squared. Anybody got that for me?
Uh, 48.
48.3.
So this is about 1.5 Gs, right? Because a G is 32.2. So you can see the best we can accelerate is about 1.5 Gs. And what we're limited it by is 1, this coefficient of friction, and 2, this downforce. If we could get the whole car, we had a 4-wheel drive car, for example, this value would be equal to, so with 4-wheel drive, it would be equal to 2.5 G's, because that's what our normalized coefficient of friction is. So that's why.
All right, so let's get working on that.
Yeah, so
Mr.
that's why
Sorry.
that's an interesting value, right? That's your best Excel you can do, right? So that's so when you're thinking about, and our drivetrain team should be thinking about this. There's no point of putting any more torque into our tires that will generate more than 975 pounds force. At that point, you're just spinning our wheels, right? All right.
Wouldn't you want to do a though? Or
Say that again?
remember earlier you said you designed for a little extra, so if you want, you could spin it, or
Yeah, you
You
want to
just
go a
need
little
to add
extra,
a
right?
bucket?
Because these are kind of fudge. We don't really know, you know.
or
Could
just-
be it could be different conditions, right? Stuff could change, right? So you always, you want to build in a little margin of error here. 10%, 5-10%.
as long as okay, just ballpark or depending.
Just for generally in engineering, it's just like best guesses are about 5%. Unless you're
Okay.
space folks. Okay, so let's see how long if we can excel at 1.5 G's for 246 feet. How long does it take us to get there? Right. So, so our delta X. So we know that we know a couple of things, right? We know X is equal to the acceleration times time squared over 2, and we know that the velocity is equal to the acceleration times time. Those. This is just a constant acceleration equation. Nothing fancy. So here, our time is going to be equal to 2 times the distance over our acceleration. So what do we get for a time here? And I'm curious also, what's our velocity at that time?
Back.
Is anybody calculating it?
Like 10 seconds? About?
10 seconds?
Yeah. Oh, actually,
No way.
let me double check my math.
I mean, maybe you're right.
I mean, the distance is 246 for us, right?
Yeah, I think it's 246. Oh, square root it.
10.1. Oh,
Don't forget that little. See what you do on the fly.
3.2.
3.2. Okay. And what's our final velocity at that point in time then? What's 3.2 times 48.3?
154. Well, that's
Okay. And so if you multiply this by 0.68, how many miles per hour are we going at the end?
104.
304. What?
104.
104 miles per hour. All right. So this is our next best model, right, folks? So we're saying our velocity versus time looks like this, right? And the slope of this line is our acceleration, which we're saying we're going at about 1.5 G's. Not bad. All right. Anybody see anything? I mean, this is fast, right? 3.2. Anybody know what's the best form? What are the best formula teams doing right now?
Acceleration.
It's been so long since we've been to a comp, we don't even know what times are reasonable, huh?
Just throwing out numbers.
It's probably like, I think it's probably like 3.8 or something. Does that seem reasonable to folks?
For one of the teams last year, I think it was 3.38 seconds.
They got 3.38, huh?
Yeah.
That's pretty good. All right, so
Over what distance?
like the Excel distance, I think it's 246 feet.
Around, that was 256.
I could be off by a little. So the best time is 3.38. I don't know if I believe that, but we'll look that up. Okay, so what's wrong? I mean, because basically that means they're going 104 miles per hour at the end of their Excel run. Does that seem reasonable?
No.
No.
No, does not seem reasonable. So so we messed something up a little bit, right? I mean, the model's not completely right. So you can't accelerate to an infinite speed, basically, right? We have a max velocity. So the next question might be, well, what's our max velocity? What's Vmax? What's the fastest with these specs that our car can go? And there's also, I mean, one thing, can someone else think what's wrong with, so I just assumed the downforce on my rear tires is the same as it is when it's static. Is that a good approximation?
No,
No.
Why not?
because you have to overcome the static friction, and then you have kinetic friction.
I was thinking
No.
about different.
When you
Go ahead.
accelerate, your center of gravity is more back.
Yeah, I mean, your center of gravity does not move back, but your weight transfers, right? You get
Sure.
you get like the center of gravity is a function of the mass of the car, right? So it's like the mass isn't really moving around on the car, but the weight shifts. So if we actually wanted to do this problem, basically what you would say is,
Your front tires matter.
so what you can do, right, is you guys have done this over and over again in your life. You said sum of the forces equals mass times acceleration, right? You maybe have never done sum of the forces minus mass times acceleration is equal to 0. So for kind of simple dynamics, this is actually kind of a crazy powerful formulation. So what we can do here is we can figure out what is the weight shift onto the rear tires during a 1.5G acceleration. So we're accelerating forward. Because we're accelerating forward, we have to draw this vector backwards with the minus. So we call this minus m times a vector, right? And we have the weight on our car, and we have, let's see here. We have the normal in the rear, we have the normal in the front, and we have the force of our tire. Everybody buy that?
Yep.
So what I'm going to write now is I'm not going to say sum of the force is equal to 0. I'm going to say this, sum of the forces minus mass times acceleration is equal to 0. And I'm going to do it, sum of the moments about the front tire, right? And I'm going to say that, let's do that counterclockwise as positive moments. So just the way sum of the forces, we can also sum the moments with this, using this method. So what we're gonna do basically now is, so around this front tire, what moment does so around this front tire, what moment does this force on the tire generate?
0.
0. It goes right through it. Does not help with the moment. Okay, that's good. So, but we have positive, we have the mass times acceleration vector, right? Times the height of the CG. That's the moment arm here. get the height of the CG, right? And then we have the weight. This is, so we go back to our, these diagrams, right? We talked about the car. So this is the length of the CG right here. This is wheelbase minus length CG. Sorry, I'm going fast. So we have weight times wheelbase minus length of the CG. That's the moment arm here. Plus, or we're gonna have a minus sign, minus the normal force in the rear times the wheelbase. So this is all gonna be equal to 0. And it's a little, normally the sum of the moments are not equal to 0 in this case, right? It's a non-equilibrium problem, but we've fudged it. We took our dynamic equation and we made it equal to 0 so we could use the process that we'd like to use all the time and say sum of the forces, sum of the moments equal to 0. Okay? So at this point, what I care about is the normal force in the rear. I basically just told you, I said, you all went along with me with that kind of bogus explanation about the normal force in the rear with no weight transfer. So I said, well, let's do one better. So we got the normal force in the rear. It's going to be equal to all these other terms, mass times acceleration times height of the CG, plus the weight times the wheelbase minus the length of the CG, right? All over the wheelbase. So there's your normal force in the rear, right? You have the contribution from weight shift. This is the weight shift contribution. So we could say this is mass times acceleration. So in our cases, so we have mass. So we can accelerate at 1.5 G's, right? So this is equal to we said about 1.5. So we said this was about 1.5 times our weight times the height of the CG over the wheelbase, plus we have the weight times wheelbase minus length CG over wheelbase. So this is, so I put this, so this here, this is your weight shift. This term here is your static weight distribution. Right? So this just depends on where your CG is, right? So if your CG, the length from the back of your tire is 0, you're basically all your weight's on your rear tires, right? So that's great. So if all you care about is going forward, you should put this CG right over the top of your rear tire, right? Put all your weight on your back tire, right? I mean, you could also, and you can see the weight shift helps you in this case. So normally the weight shift doesn't help you that much. And how can you increase the weight shift? You can increase the height of your CG, right? So we increase the height of our CG and we can decrease our wheelbase. But in practice, you never do this, right? There's so many better reasons to keep the height of your CG down that you would never bring your CG up just to help with weight shifting towards the rear of your car, right? You know, but if all we did, you know, like a dragster does not put the CG in the center of their car like a formula car, right? A dragster puts all their weight on top of their back driving tires, right? So I mean, that's how you see a little bit of a difference there, right? So if you want to do a little bit more accurate model, you could use this for figuring out what's the best acceleration you can do. You can see it's a little bit more complicated, I would say, than doing it the other way. But this other one got us in the ballpark. 1.5 Gs. You might be able to go 1.8 because we're not including weight shift. Maybe 3.38 seconds. The next question was, what is max velocity? What's the fastest your car can go? I know, I mean, you could drive a shit, you could design a shit gearbox and, you know, that could limit you. And there's a lot, you know, you could have a lot of different things, but let's say we haven't designed the gearbox yet, just based on the specs of our car. What's the fastest we can go?
45 miles an hour.
So Bill's got intuition, 45. Is there anything that maybe there's some stuff that we could use from previous discussion today to look at it, right? So we started off today, right, relating power as a function of velocity, basically, right? So what we can do is if we know the max power, we can find the max velocity, right? And if we know some of these values. So what we'll basically do, so if we know that at top speed, our power is equal to mass times our acceleration times velocity, at this point, we're not accelerating. We're just getting as fast as we can. Plus, we have our rolling resistance times our weight times our velocity, plus 1/2 rho CD A frontal B cubed, right? So we need to solve for velocity in this case. We have this cubic function. So so 1 horsepower, by the way. So horsepower is kind of an odd term. So 1 horsepower is about 550 foot-pounds force per second, which is a more useful unit of power for us than horsepower when we're actually doing analysis. Horsepower doesn't really convert to anything. So if we have 60 horsepower times 550 foot-pounds force per second per horsepower, these will cancel. Our rolling resistance is 0.01. Our weight is 650 pounds force times velocity plus 1/2 the density of air, which we need it to be in slugs per feet cubed in this case, is 2.38 times 10 to the -3 slugs per feet cubed. Our frontal area is maybe 11 feet squared. Just get us in the ballpark here. So this is rho CD. Oh, and our CD was maybe it's going to be on the order of 1 for us, to be honest. But I don't know. Let's just put it on the order of 1 for now. This is CD. Like it depends. This depends a lot for race cars, right? Like if you need a lot of downforce, your CD is going to go up at the expense of getting downforce from your aero package. If you don't care about downforce, you can get your CDs down to like 0.7 or something, right? So this.
Or what do you put for ours?
I just put 1.
Okay.
It's going to be between 0.7 and 2. Right? It's not going to be outside that range. That's why they put this 1/2 in there. All right.
Are you calculating drag here? Is that what you're working at?
Exactly. So this is power drag.
What about frontal area?
And that's this 11 feet squared.
Yeah, pardon me.
And this is power rolling resistance, and this is power of our engine. So basically, the only thing we don't know right now is this velocity, right? So now we're going to calculate what's the top speed our car could go if we do everything in the drivetrain right. We're just limited by these 2 values. Does anyone have some cubic function solver here? Or you can at least just give the if you give me all these terms, I could put it in some like cubic function solver and we could solve for velocity, right? Because the hard part here is we have v cubed.
I got 72.9192.
For velocity.
Yeah.
You know what units you get it in?
Let me find out.
No, it's feet. It should come out in feet per second.
Oh, okay.
So if we know there's I think we mentioned before 1 foot per second is like 0.68 miles per hour. So if you multiply this times 0.68 miles per hour for every 1 foot per second.
I got 49.58.
Bill had a pretty good guess right off the bat, right?
45.
Pretty close. So this is basically saying that our max velocity is 49.58 miles per hour. I mean, this is surprisingly slow to me, to be honest.
I think so.
I mean, the car ain't that big.
For safety.
I mean, because this is basically saying you have an infinite runway too. This is not saying at the end of the Excel track. This is basically saying how fast can this car go if we just let you get on it on the freeway. So this is low in my mind. Like, I'm surprised. I think it should be faster.
I got a higher value, but I got 134 feet per second.
Yeah. So I think this value is probably closer to our top speed after the Excel run. But if we just put this thing on an infinite runway, I think you could go faster personally. I mean, you got a 60 horsepower engine on 600 pounds. I mean, you don't got that much drag. But so how many miles per hour is this?
91. 91.12.
So we've kind of established some bounds for the best we can do already, right? So our velocity versus time. I mean, one thing we know is we're capped at 91. We're never going over 91. We know that we can never excel over 1.5 Gs. So this slope, 1.5, right? So I'm kind of the best we can think to do at this moment is something like this, right? So but maybe our 100-foot time was probably going to end here anyways, right? So 100-foot time, we're just not going to have enough time to get up to that speed basically. But this is kind of the best you can do. And we can start to see, right? Like we saw how the coefficient of friction between our tires and the ground is pretty critical. We also can kind of see how the power of our engine plays a role with drag and rolling resistance. I mean, one reason why this value, this force max on our tire is important is because we design for it everywhere. So it's not only a system design, but like if you're designing the drive shaft, like this can help you calculate what's the max torque, right? Or if you're designing the suspension, like this is the max longitudinal forces on your suspension, right? So this value is used all over the place, right? And so understanding how you can take this friction value to get forces to help you do your design is pretty critical. Baja is a little different in that they run into rocks, right? So like they might see some bigger forces here and there just from sitting from rocks. But okay, so last thing. So we talked a little about weight shift, a little about all this stuff. Last thing I want to talk a little about is, okay, so we said that the force on the tire times the velocity is going to be equal to the power, right? But we also said that this force on the tire is the mass times acceleration. mass times acceleration times the velocity is equal to the power. So that tells us also that we kind of have a power limited acceleration too. So before we talked about a traction limited acceleration of our car, right? It was based on the coefficient of friction. This one is based on our engine. So the max acceleration we can get here is going to be the power divided by the mass times the velocity, basically, right? So in this case, we had 60 horsepower times, I forget, 550. 550. And then foot pounds force per second over our mass in this case is going to be 650 pounds force divided by 32.2 feet per second squared times our velocity, right? So what is this? So what does this value work out to be? So this is 1634.8 over velocity. And this cancels the horsepower. Pounds force cancel. One of these seconds cancels with this seconds. And so here we're going to get
The feet squared.
feet squared per second. Actually, these don't cancel. They get cubed. They all go together. All right, so but we want to solve for velocity versus time, right? We want to put it on this graph. And folks, just stop and ask me questions here, right? So this was just the power of our engine, force of the tire times velocity, and we just knew that the best that can do is help us do our mass times acceleration, right?
Right.
Got it. Where's everybody at? Patrick? Oh, on the previous equation, I multiplied them instead of added the right side, so that's why.
Got you.
Chris, you know, all these numbers you're putting in here, that's not include the driver.
I'm the 650 pounds for the car. I was assuming, so our car last year was 550, I thought. And so I figured with the lighter engine, we'd get the 500 and then we could add 150 for the driver.
Okay.
That's my best. That was my reasoning basically.
Oh, okay.
Nothing more exciting than that. All right, let's check who's awake. Hour and a half in.
Oh, the car last year was
Been a
490.
good minute, huh?
Oh, the car was 490 last year? Well, maybe
Yeah,
maybe
with
we got a little
Christian.
faster than this.
It was like around.
Yeah, so with Christian it was 670 plus 180. Maybe a little more now, so this looks accurate.
Where is Christian?
Sleeping.
He's here.
He's in the chat.
He's here. It said this answered.
Okay.
answer too.
All right.
Sleepy boy.
If someone's awake here, I want to get velocity versus time. What type of equation is this?
Me. Alive.
PVA.
PVA.
So,
How'd you know?
so how do I solve for velocity versus time using this equation?
Do you plug in your acceleration?
Well, is the acceleration independent of the velocity?
No.
How is the acceleration
integrate.
related? Yeah, it's the derivative. So if I wrote it like this for you instead, what does that look like to you now?
Integral.
Well, this is some derivative.
Equation.
A differential equation, right? This is why we force you to take the class on ODEs basically, because no matter where you go, stuff boils down into an ODE. So we can do our little. So we have velocity times dv is equal to 1635 times dt. Right? And so we want to solve for it, right? We're going to integrate both sides. Right? And so here we're going to get v squared over 2 is going to be equal to 1635 times time.
And yeah, and that'll give us feet squared over second squared.
What about the constant? Because it's indefinite.
Infinity.
That's a good question. We can assume that the initial velocity is 0 and the initial time is also 0 though. So we're kind of fudge factoring that a little. That's a good point. But there is a feet cubed per second cubed here. So I've never even this is the first time I've ever even looked at this. I'm honestly thinking about it right now. So this tells me that the velocity is equal to so this is 3270 t times feet cubed per second cubed.
Can I ask why it would be feet cubed?
To be feet squared.
Feet squared.
Okay, cool.
You could ask, and the answer would be because it's not. Right. So let's try. So I'm just gonna try something. I have no idea how this is gonna turn out. So let's just try something. Could be a major crash and burn, but let's bust out our Excel here. You still with me, Juan?
He's asleep.
Juan couldn't hang?
What are you talking about?
He dead.
I'm dead. Get out of here.
All right. So this is our best car runs. Can people see what I'm doing?
Yeah.
Yeah.
All right. So time. We're gonna start at 0, and we'll step up in 0.1s, and we'll go to about 10 seconds. 10 seconds. So here, this is our traction. Here's our traction limited speed. So in this case, and so this is our acceleration was 1.5 Gs, right? So this was the 48.3 feet per second. Right?
Yeah.
So this one's going to be 0. And so let's add this. So these are all 3 going to be velocities. And so this one's going to be equal to the time difference, this minus this. So delta t times our acceleration times this value up here. And we're going to have to add our previous speed. So this is basically numerical methods. This is what you call an Euler integration. Same dude with all the other Eulers. But basically, so this term right here is just basically, so this is the acceleration. This is derivative of velocity over time times this left-hand portion is change in time. So dv dt times dt is just dv plus the old velocity. So we do this down. So sometimes you need to, this one needs to stay constant, right? So when you put these little money signs, basically it means that in every single time, it's not going to allow this to change, but it's going to change everything else. So here's our traction limited speed. Here's our propulsion limited speed, propulsion limited. Right. So in this case, we said it's going to be equal to the time square rooted times, what did I say it was going to be? 3260 or 70?
60, I thought.
60. Close enough. This is also raised to the 0.5. And here's our max speed limited. So this one is just always, what do we say it was in feet per second?
190.
What was it? Let me check.
Max speed.
It was
91.
Yeah, 91 miles per hour and 134. 134. All right, so let's see what these different graphs show us. So we're going to insert. Let's do this. Okay, so this is interesting. Ah. Okay. Ah. Okay, so early on, very early on, we're traction limited, right? Can everyone see this?
Yeah.
So the fastest we can go basically is we're limited by our wheels, right? Wheels, 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 until we're limited by our engine, right? Boop, boop, boop. Can't go any faster with can't do any better with our engine, engine, and then we're limited by our top speed, basically our max power output of our engine, right? So let's get the best we can do. So this is at, so up to about 1.4. Let's combine these into our best. So our best at first is traction limited up to 1.4, right? So this is until this, yeah, up until, or so which one's the lowest basically? So this is the lowest until now, this one's the lowest. So first we're limited here, and then up until about 5.6 seconds, we're now limited by our propulsion. It's gonna be right here, 5.6.
Yeah.
We're limited by propulsion, right? So that's about here. Oops. got to paste values. Paste values. Copy, paste values. Okay, and then we're going to reach our top speed. Whoops. This one's going to be 134. 134. All right, so let's include our best. So here you can see so yellow is our best, right? But first it follows the blue, then it follows the orange, and then it follows the gray, right? So if we want to get our distance of our best round, let's see what our distance versus time starts looking like. So this is velocity versus time. So our distance is going to start off at 0, and then it's going to go this change in time here minus here. So that's our change in time times our velocity plus whatever we did before.
You'll notice I was not here over the weekend.
Hey, can whoever that is mute?
You'll notice I was not.
All right. So here's our distance versus time. So let's see if, I don't know if there's an easy way to do the scatter plot. So data, insert, scatter plot. There you go. That gives us those two. So here's what we can shoot for. Right? So, wait, I did something wrong. Why does this go 0 to 20? 0 to 100.
It's probably off. Oh, it might be because he selected the whole column.
Yeah, let me just do it this way. I'll have to go a little manual with it. That looks better, right? So if I was looking for the 246 time,
Whoever's watching cartoons, can you please mute?
get them, baby. Well, I could just come right here. So 249. So about 3.6 seconds is about what we can do, right? I mean, we could improve. There's some things we could improve here, right? We could improve the weight we could reduce the weight of the car. We could get tires that are more grippy. We could get the power of our engine up, right? So this is kind of basically what can we expect our straight line drive to look like at this point. And this is right. So this is distance and feet versus time here, right? And this kind of summarizes the different ways you can be limited, and the different areas during Excel when you'd have those limitations. The early, right, was traction, right? The next portion is you're limited by the propulsion of your engine, and then you're limited by the top speed, basically, right? Which is also a function of your engine, right? But it also, this yellow line is not really including as much of the drag and that sort of thing, right? So it's basically the kind of, this is what it would kind of look like if you included the drag. I mean, it might even take longer to reach this top speed, to be honest. In real life, if what we'd have to do is, I'm going to share this other screen. Stop share this one. I'm going to go to.
You're gonna record these?
Yeah, I'm recording it.
Okay.
Or I have been recording it. So. So right here, So instead of solving that simpler differential equation, we could have solved this whole differential equation, right? So this is this whole differential equation, but it's pretty complex, right? Because it's a nonlinear differential equation, right? It's got a v cubed in it. So I don't even know how to analytically solve that. I'd have to plug this into a MATLAB program or Excel and do this numerically. So it's not the other one. The reason I kind of got rid of these other two terms was just to kind of do best case scenario. All right, so let's do a little summary. So summary of today. Right, we talked about forces on the car. Right, so you had your car. We had a normal force in the rear, a normal force in the front. We have the weight at the CG. We have a drag force. We have a rolling resistance. And we have a force of the tire. Right, so we have all that, right? We said that the sum of the forces, and we'll say in the x direction, equals to the mass times the acceleration, right? And so we said this was force tire minus force drag minus force rolling resistance, right? And we said, hey, we can isolate this force drag here, or sorry, the force on the tire. And we could say that the force on the tire times, and multiply everything by velocity, is equal to mass times acceleration times velocity plus the drag, which was 1/2 rho a frontal drag v cubed now times the rolling resistance plus the coefficient of rolling resistance times the weight times the velocity, right? And this whole thing was the power of our engine. Right, so we talked a little bit about that. We then said if you have this kind of simple model of the car, we talked about the traction limited case. Right, and so we asked ourselves, what was a max? What was the max acceleration for and rear and front? And we said, well, the force max was equal to the normalized force in the longitudinal direction. And the max of this, right, times the downforce in the rear. We said this would result in a mass times a max. And the mass in this case is nothing but the two normal forces, right? Those two added together. Divided by 32.2 feet per second squared. So times a max. So that basically meant that our so this term right here, a max, sorry, a max was equal to the normalized longitudinal force times the downforce you have in the rear over the total downforce. What's this? And this is in G's, right? So basically in this case, if this term was 1, let's say you put all the downforce in the rear, like a dragster, right? Put all the downforce in the rear. So like say this would be like 1 for a dragster, right? It's like 0.6 for us. Pretty much both teams, right? So you're kind of in that case limited by this drag, this tire grip, right? And so that's why it's important. If we go pick tires, we could come to the tire data that the tire consortium takes, right? And they plot this for all the different tires, right? So you can pick what tires have the best normalized longitudinal force. And we pick it for the downforce that we have, right? So we talked about that. We also talked a little bit about weight shift, right? So we talked about how you could in this kind of simple 2D model with the weight and the force on the tire, we could do sum of the forces minus the mass times acceleration is equal to 0, right? In this case, we draw this vector, and this is mass times acceleration in negative direction, right? Pretending like it's actually accelerating forward, right? And we could then do we could do this, and we could do some of the sum of the forces times distance minus, well, let's just do this. Sum of the forces minus the mass times accelerations times its distance. Right, is equal to 0. And so this was forces, and this was moment. Right, and that was a nice trick to find forces in a dynamic situation where normally you guys are pretty much used to handling equilibrium scenarios, right? Where acceleration is 0, everything's moving at constant velocity. Then we finished talking a little bit about being power limited by propulsion, right? So then we talked about propulsion limited. Right, so in the case where we were propulsion limited, we had that our power max would result in mass times acceleration times velocity plus mu r times the weight times the velocity plus 1/2 rho a frontal drag coefficient v cubed, right? And so we wanted to know our top speed. And this doesn't necessarily need to be max in this case. It's only the max speed that we have to do that. So p. So top speed, if we put in our max power, so we put in p equals p max. We say our acceleration is 0 because we've reached a top speed. We say our p max is going to be equal to mu r times the weight times the max velocity plus 1/2 rho a frontal drag coefficient v max cubed, right? And so that helps us connect. How does the increasing the power of our engine help us increase our max velocity? It also can tell us the effect of our drag coefficient on our max velocity, right? And then let's see here. So I'm gonna stop sharing. And then lastly, sorry, just fiddling around with Zoom over here. And then lastly, right, we talked about this. Right? We talked about these different scenarios and when they come into play, right? So this is time. This is time versus our velocity, right? And so we said early on, we're traction limited by this blue line, basically. We're pushing our tires right up until they start to spin. Then, once we reach a certain point, our engine can no longer keep spinning our tires, right? We just don't, we don't have enough power at that velocity to keep the torque up that high, basically. So our torque falls off that max value, and then we start getting limited by our engine, right? And then we start to get limited by our drag and everything, right? And so these are kind of some of the things that are going to govern basically the speed of our car. Right. And so here's maybe and we've created more complex models than this of the acceleration of our car because maybe some things we forgot, right? The car has rotational inertia. you need to spin, the wheels need to spin up, all your drive shafts, all your gears, they got to spin up. So we've neglected any rotational inertia in our system. We've neglected the fact that our gearbox does not keep us at our peak power the entire time. I mean, that's the point of the gearbox, is to keep us as close to our peak power at all times. But we end up shifting around peak power, right? And so we can't sit at 60 horsepower the whole time, even if that's our engine's best, right? We're gonna be below it, we're gonna RPM up to it, we're gonna go over it, drop off peak power and go back down over and over again, right? So we haven't included anything like that. But other than that, you know, this is kind of a reason, kind of a first guess, and you can see that, you know, it gets us a little bit of analysis gets us in the ballpark of what the best teams are doing, basically, right? These 3.5 seconds. I mean, they're also lighter, so you know, we'd have to run these numbers again for a car that's 100 pounds lighter. They might also have 100 horsepower, right? So that'll change things. But yeah, so we'll plan to kind of continue like this, and like today we talked kind of a lot about straight line stuff. Next time we'll talk a little bit more about cornering. Then we'll talk a little bit about suspension geometry, right? So first I'm just gonna start really kind of abstract like this, just kind of high level stuff. How do you look at the car? And then we'll start looking about more specific stuff in the suspension. And then we'll work our way from the suspension to chassis. And then we'll work our way to probably drivetrain and brakes and that sort of thing. And actually after suspension, we'll be steering. We'll have to talk a little bit about just general stuff about steering. So I hope this was somewhat useful today.
Very helpful.
Yeah, thank you.
So yeah, and then you should think of questions. Like, you know, I don't necessarily want to just talk about theory unless I think the theory actually helps you make design decisions, right? So you should, you know, if you have a specific question, you know, like, how do I pick the gear ratio or the rack of my steering, right? I don't know any of these, but we could start to, you know, fudge around with it. How do we pick these things? So if you have kind of questions that have come up, we could talk, you know, about how you design it. This would just be a good place to, like, all right, let's see what a little bit of, you know, back of the envelope calculation tells us what, you know, what ballpark should these values be